So let's talk about making the dream a reality. What does project progress really look like? This is a top-down photo, a little more clear than what I gave you in the first overall photograph of the work site. And as I go through this, I will try to mention some of the ITER members to show you what an integrated international project this really is. So in the ITER switchyard here at this end, many of the components there for the first part of the ITER switchyard, which is the steady state electrical network, were supplied by the United States. There's also in the lower switchyard here, there is the Chinese supplied transformers. There is electrical equipment, really more than a hectare of electrical equipment supplied by others. Then that part of the switchyard, which is called the pulse power network, has input to these two buildings that we call the power conversion buildings that will convert the incoming AC, alternating current, to direct current at exactly the right amperage that it can power the ITER magnets. There's also cryogenic fluid, liquid helium, flowing through the magnets because the magnets have to be superconducting, and to do that, they have to be at minus 269 degrees. So in the tokamak, you've got 150 million degrees, the hottest point in the universe, inside the magnets that are containing the plasma. You have from the cryo plant about 4 degrees from absolute zero, the hottest, the temperature of interstellar space. So those systems are vital to making this all work. Now, you've also got some manufacturing facilities. Here, the PF Coils facility. This is to manufacture the colloidal field magnets that are too large to travel by road. And then the Cryostat workshop, the only building on the work site that is owned by India, because India is making the overall thermos that will encase the cryostat, that will encase the overall tokamak. It's being made in 4 large pieces. 2 of them, I'll show you later, have already been installed here in the tokamak pit. One of them, all the way at the top, there is the upper cylinder. That one is finished, but still in storage, waiting for its turn to be installed. And in the Cryostat workshop today, India is still putting together the final piece, which will be the lid, the Cryostat lid that goes over everything. All of the components from all the ITER members arrive on the work site by that road that you can see at the far. They come on in, they're stored in some of the temporary storage buildings. Eventually, when it's their time, they go through this cleaning building at the back, and then they go into the assembly hall. We'll talk about the assembly hall and all that works. The cranes pick up the equipment, carry it into the tokamak building, and deposit it directly into the tokamak pit. And at the far, you can also see there is the radio frequency building with 2 of the heating systems that will be ready for first plasma. Down here, another heating system, the neutral beam power supply, is being built to full scale now in Italy, and it will eventually come after first plasma as the 3rd of ITER's heating systems. Then if you have heat, if you're manufacturing all this heat and manufacturing with fusion, you have to have a place for that heat to go. In a commercial plant, that would be the turbine generator, right? Which would convert the steam to electricity. ITER will not make electricity, but ITER will have this essentially giant heat exchanger, the heat rejection system, capable of taking far more heat than ITER is actually designed to generate. And the heating system then will make sure that any water before it is returned, we get our water from the canal up above this hill, and before it's returned to the canal, that there is no temperature differential. The other building that I would mention is simply the control building at the far left there. That is still in preparation. I've talked about the tokamak building, but the tokamak building that you can see here is actually 3 buildings in one. Here you have the diagnostics building, then the tokamak building, and then on the far side, the tritium building, which will not be ready for first plasma, but I'll show you a photograph. Work has resumed on that. Tritium building is one of those. And together, the diagnostics building, the tokamak building, and the tritium building comprise the overall tokamak complex. So what have we been doing recently? Much of this now is just from about the past year, maybe a little bit more, where we have been doing installation. The first component, which to be installed in the major component, to be installed in the tokamak pit, is the Cryostat Base. And you see that right here. This is the bottom of that thermos that I said India was putting together. So that 1,250 tons picked up by these overhead cranes and transported across so that it can be deposited in the tokamak building in the tokamak pit. Now, that might seem simple, but here's something to remember. This is the top-down view as it was installed in the pit. That Cryostat Base, now on the top-down view, is 30 meters in diameter. Okay, so immense, 1,250 tons, and yet the precision with which it had to be stationed in its final position was under 3 millimeters at every one of the metrology points. Why is that important? Talk to an engineer and they'll tell you that that sort of engineering is unbelievable. So what we are doing at ITER, yes, our goal ultimately is fusion power, demonstrating that fusion can be done at industrial scale, but for any type of magnetic fusion device globally, for any project going on, for any national project, for any fusion roadmap that any country has, ITER is providing value by proving that fusion engineering can be done at full scale. The next component, the cryostat lower cylinder. So again, this is the thermostat, and this is essentially just a circle of metal, but an incredibly precise circle of metal. Again, 30 meters in diameter, the same as the base, 10 meters high. That essentially means that this component was about the size of the prehistoric monument at Stonehenge. Yeah, the ring at Stonehenge, if that gives you perspective. And again, that was lowered in just a few months after the Cryostat Base. In January, we lowered another component, which we sometimes talk about as the jewel. There are multiples of these. This is a very, very shiny component made by Korea. It's the thermal shield comes in two types. This type is insulating the thermostat from the cryostat from the interior of the tokamak, and it's metal, but with a silver plating that helps it to be ultra reflective. I'll tell you about another one a bit later. But we don't always talk a lot about ITER innovation. And here's a good example where Korea is using the insights. They're making the thermal shields. They're using the insights that they took from manufacturing the thermal shield to improve shipping containers for liquefied natural gas, which again have a similar parameter, which is you want to keep the cold in and the heat out. And their experience in working on ITER helped them with perfecting that. Now, on the top picture on this one, you see us getting ready to install ITER's magnets. This was early 2021, several months ago. Actually, most of the welding was finished even in the last few months of 2020. But this is where the welding had to be completed, where we're putting the first two components together, the lower cylinder to the cryostat base. So really about 90 meters of welding done partly by humans and partly by robots. The first magnet was installed in April. This is poloidal field coil number 6. And you know, you're going to see another photo of this later. So remember PF6. PF6 doesn't look so big here, right? Because it looks like it's kind of small, you know, sticking into this. But that magnet is 10 meters in diameter. It's huge. It's incredibly weighty. It was procured by Europe, but Europe procured it in China because they were doing many PF6 magnet or multiple PF6 magnets at the same time. So there you see PF6 as the first magnet installed in the pit.